Hey class, today we're going to take a look at an important concept in Unit S, simple linear regression. It's dealing with outliers. Those are the points which are far away from the regression line, and they can significantly change the equation as well as the r squared. So let's take a look at that. And the two problems that I'm going to use are from Unit S, page S6. That's the ages and push-ups example. And you also saw that in Unit C. And then a new one, which is on page S7, which is dealing with house sizes and house prices. So we'll take a look at those two there. So on page S6, we can take a look here at push-ups and ages. Remember that age is the x variable and push-ups is the y variable. If you haven't looked at the class notes, go and take a look at those and read through the parts that go through the calculation of the regression line by hand, as well as the r squared value. And it does that for both page S6 and S7. But we're going to take a look at this in Excel and talk about the outliers and how we can get rid of the outliers. This is going to help you with your assignment, particularly question number 3. And the other place that it's mentioned in Unit S is right near the end, just very briefly, on page S23 at the bottom there. But we're mostly handling this then through the lab. So let's take a look then at the outliers first of all. And probably the best way to show you the outliers is to draw a simple graph here, or I'm going to let Excel actually draw it. So I'm going to highlight the data here. I'm going to go into Insert. Of course, you might have a little different setup here because I'm using a Mac, but the PCs are pretty close to being the same. And I'm going to go down here to types of charts, and in particular, one called an XY scatter plot. And I'm just going to choose the first one here. It looks like that. And so this is what we've got here for the push-ups and the ages. Now I can, just as an aside here, I can change or add some chart elements here. So I can add an axis title. So the primary horizontal, I could change that to be age, and then I can add here a vertical, and we'll call that push-ups. You probably want to give this some good name here. I'm not going to do that. I'm just going to get rid of it. You can add a title here. I'm also going to add here a trend line. And it's going to be a linear trend line. So there's our sample regression line that we calculated by hand on page S6. We can actually even add the equation. I'm going to go back up here to adding a chart element. And under the trend line, more trend line options, and display the equation on the chart right here. So there you go. Right? Now you can also do any of those things here. If you have trouble finding the menu, you can do any of those things here by right-clicking, say on the axes, and you can format the axes and the titles and things like that. And on this line here, we can, if you get it right, you can format the trend line, and that will bring you back up to this little menu here where we selected display the equation on the chart. All right, now let me show you actually the results of the regression. I've already done that, and then we're going to come back and we're going to do it, and we're going to knock off the outliers one at a time. But let me show you the results at this point. So this particular page here, so here's again the age and the push-ups, and here's the chart here. I didn't actually put on the trend line here, didn't put on the equation, but we've got it below here. So this is the summary output that we have here, and I just want to point out a couple things. First of all, the r squared value is 0.398, so 40% of the variation in push-ups is explained by age. Down here we have an ANOVA table, and when you're talking about a simple linear regression, you're not getting any more information out of an ANOVA table than you are from just the age line itself. And the reason is that the ANOVA takes a look at all of the x variables together as they explain the y variable. So in our case, we only have one x variable, which is age. Now, it has a number of different observations. I'm not talking about the n. I'm talking about the number of x variables, and the symbol that we use for that is p. We'll see that later in the notes. All right. So when you only have one x variable here, then the ANOVA results actually mirror the t results down here. Let me show you. If you take a look here at the f star value for the ANOVA, it's actually the square of the t star value for age right here. So that's kind of an interesting observation there. The other thing here then is the critical value, and the critical value here is not shown here for the t star value, but if you were to square that, you get the critical value for the f, which is also not shown. Over here, I've got how you would calculate the critical value if you needed it using an f inverse right tail function. And the arguments are alpha, and then your degrees of freedom for your numerator, which is for SSR, which is p, the number of x variables. Now again, this is all going to be talked about in class if you haven't looked at the notes yet, and I might need a day or so in order to get them all up. And then the denominator there is 10, which is right here. So that's the SSE, or another name for that is residual, right? So the SSE value, which is n minus p minus 1. So we've got 12 observations minus one x variable minus 1 for the y variable. And so that gives us then 10. And the p-value then turns out to be 0.028. So that's significant at a 5% level. And here's the function that we would use. It's an f.dis.rt. The arguments are the 6.61, which is this f star value right here, and then the same degrees of freedom as we had for the critical value, which are found right here. So 1 and 10. So that gives you then 0.028, and that says that that's your alpha, that's your p-value, pardon me, and that is less than an alpha of 5%. So that means that age is a significant determinant of push-ups. Before we go down here, I just want to go back up here and say, if you took the square root of r squared, and this only works when you have one x variable, so for a simple linear regression, if you have more than one x variable, then it's not quite the same because there is a correlation between each pairing of variables. But this guy here, you probably recognize this. If we were to put a negative in front of that, that's the r that we calculated in unit C, and then again at the bottom of page S6. That's the Pearson R, the correlation coefficient between x and y. Now, it always shows up as positive up here, but what you do is you go down here to the slope coefficient. So this is your B1 value, and it's negative. So if it's negative, then this is negative as well. All right, let's take a look at the bottom here. And we calculated these guys by hand. So there's your regression equation for the line. It's y hat, or push-ups hat, is equal to 32.862 minus 0.265 times x, or age, right? And then we've got so those are the B naught and the S and the B1 values. Here's the SB naught and the SB1 values, which I'll show you to calculate by hand in the notes. So that's the standard deviation of each. Now, if you divide 32.862 by its standard error, so the B naught divided by SB naught, you'll get the T star for the intercept. And it is a p-value of 0. And here is the confidence interval for the population beta naught. Remember, B naught is an estimate of beta naught, and it is significantly positive, which is what we would expect, of course, with a negative slope line, is that the intercept will be significantly positive. And so it goes from, we're 95% certain that the intercept is somewhere between 22.183 and 43.541. Same kind of animal down here. This is for the age, so this is your B1 value. That's your slope, which we calculated by hand. Your SB1, which we'll also calculate by hand. And if you divide the B1 by the SB1, you'll get the T star, which is significant. Now, this is assuming a two-sided test. If it was a one-sided test, then it'd be half of that, which is 0.014. And here's your confidence interval then. So notice that both of them are negative. So the interval doesn't contain 0, so the slope is significantly negative, going from 0.495 to minus 0.035. So that's how we read that. Now, the important thing here, though, is we have added this, we will add, and I'll show you how to do this in Excel here, something called the residuals. Now, the residuals, then, are the difference between the y hat values and the actual y values for a particular observation. So let's take a look at this guy right here. So this is our first point. So it's the point, no, it's not. I want to take a look at this one right here, 1934. So it's probably, where would that be? 19, oh, that's funny, it's not drawing it really well. It's off by just a little bit here. It's probably this guy right here. Well, it should be somewhere around here. You know what? I'm not sure exactly what happened. I think what happened was I saved this as a picture. It's not a chart. And so it's changed a little bit there in terms of that. It must be this guy right here. There we go. 1934. Was I reading that wrong? Okay. Well, this is actually probably the better one to take a look at here, and this is your 1934 right there. Now, what I want you to notice here is that that's above the line. If you go down here, we'll hit about, 2728, right? So 19 going up, we'd hit about 2728, and the actual observation here is 34. So this has a positive error term. Let's go over here and take a look at how you would calculate that. So if I took a look at that first observation here, which is 1934, I'm just going to move it down here so we can see that a little bit better. If I took the intercept, so 32.862 plus the slope, so minus 0.265 times the x value, then I end up with 27.87, which is, when we took a look at the graph, we said we should get a value of around 27 or 28. That's this guy right here. So the predicted push-up values are the y hat values. All right? So I can put in a y hat right there. So that's what this column is right there. Now, the actual observation was 34. So if we took the difference between those two, so 34 minus the 27.825, we get the residual, or the error. And so these are the E's, or the residuals, and here's the 6.17. So 34 is 6.17 above 27.83. The last one here, the standardized residual, is, well, if you took this value here and you divided by the standard error, which is the standard deviation of all the errors, you get a number pretty close to that. Now, there is some adjustment, which we don't need to go into, but you're going to get something pretty close to that. And so that's what the standardized residuals column is all about. Now, where that's useful is we want to take a look at any standardized residuals which are outside of the plus or minus 2 range. Remember, if we were doing a confidence interval for a 95% level of confidence, we'd be looking at z-values of plus or minus 1.96 and probably similar t-values with that. So what statisticians do is they look at that and they say, well, you know, plus or minus 2 standard deviations away from the mean of 0 for the residuals, as that's what we would expect to see when we add up all the positives and negatives. Of course, they'll all come to 0. Then these particular guys who have standardized residuals, either positive or negative, but outside the 2 range, are quite large here. They're the outliers. Now, the outliers up here are these guys, this guy and this guy. And it's actually these last 2 guys right down here. Okay, now I know the minus 1.944 isn't quite there, but I'm going to show you what happens when we get rid of the one observation here. So this is what statisticians do. Let's go back to our first page here, and I'm just going to get rid of the this chart again. Remember, here's the 2 residuals that we're going to be taking a look at here. But let's get rid of this now. All right, now let's run through doing the regression. Data analysis, regression. My Y range is push-ups, including the label. My X range is age. Tell it you got labels. Don't worry about the constant to 0. We're not going to ever use that. Don't worry about the confidence interval. But down here, I want you to click the box that says standardized residuals. Make sure that if you're doing a bunch of assignment problems in a row, that for the other ones you deselect that box, because otherwise you'll end up with just tons and tons of rows of residuals. So we're going to select that one, and then I'm just going to choose an output range here, and I'll put it up here, right there. All right. So this is the same as we got then from the page I just showed you, except that, of course, I've cleaned it up by taking it to about 3 decimal places. But here we got the residuals. And what you do here then is, I know the highest one is at the bottom, but the way that you want to handle this, especially when you've got, say, 200 residuals and you don't want to go eyeballing it all the way through, is just do a sort. So I'm going to go here to my sort button. Now remember, it's under the data tab. You'll find a sort, or under the home, oops, oh, hit the wrong button there, sorry. Or under the home tab, there's a sort over here, right? And you can sort from smallest to largest. And so what it does then is it's got this minus 1.94 there, and then the positive 2.03 here. So again, you ignore the sign, you look at just the magnitude of the numbers, and this is the one that has the greatest standardized residual, and it's outside of 2. So what I'm going to do is I'm going to get rid of observation 12. We do this one at a time. So if you had a bunch of ones that are outside of the 2 range, you don't do them all at the same time. You're going to do them one at a time. So you take the one which is furthest away. Now in this particular case then, that's observation number 12. Remember, your titles are in the first row here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we're going to get rid of those guys right there. Hey, just a note here, and that's that if you have a respondent column, I'd probably get rid of it at this point, because the numbers of the respondents can really get messed up, especially if you've taken out any blanks or anything like that. And so I would take them right out here and just do a count. Or remember, of course, that observation 12 will be in row 13 because of the labels in row 1. Okay, now let's rerun the regression. So data analysis. Everything is going to stay the same, except for, instead of going to B13, I'm going to go to B12. And then, of course, I have to do the same with A as well. And then the other thing I want to do, of course, is change my output range. So my output range then will be somewhere below this. And see, oops, what happens here. There we go. Okay. Now, what I want you to notice is that the R-squared value was 40%. By getting rid of one observation, look what happens. R-squared value jumps up to 66%. Just by getting rid of one observation. Now, I recognize that there's only 12 observations in this whole data set. And when you're talking about, say, 200 observations, there'll be a smaller marginal impact of getting rid of one particular observation. But now, let's continue on here. Notice that the p-value is much lower. So before it was about 2-point-something%, now it's almost 0. All right? Okay, let's sort the residuals again. So sort, and if you take a look at these, you'll see that this particular residual, this was the one that was minus 1.93 in the last example. Now it's minus 2.67. Why does it have a greater residual? Well, because the line was redrawn. You actually have a different intercept and a different slope here. But again, the p-values are smaller and the R-squared is larger. So here we've got observation number 11. The greatest negative residual then, standardized residual, is for observation number 11. So we're going to go up here. And observation number 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, of course, is in row 12. And delete that. By the way, they could obviously be in somewhere in the middle here, in which case you would delete it, and then you could move everything up again. Let's get rid of that, and we're going to run the regression again. So data analysis, regression. And what we've got here is, this is now going to go to B11, not B12. This will go to A11, not A12. And of course, we'll have a new output range. Let's just drop down below here. You can see if you had 200 observations, you'd have 200 rows of residuals, and that would be quite a hassle. But watch what happens. R-squared jumps up to 95% just by getting rid of one more observation. So it went from 40% up to 66% up to 95%. The regression line is redrawn, so new intercept and a new slope. Look at the p-value. Now this, of course, is in scientific notation, so it's 0.0000237, and that, of course, is highly significant. It's almost 0. Last thing that we want to do here is just do another sort, and all of these standardized residuals are now within that plus or minus 2 range. So we would stop there and we would say, we got rid of the 2 residuals. This is a much better model here. Now, we could redraw the picture here. I'm not going to do that. All that you'll notice is that the line will look slightly different here, and that it will show that the 2 points are gone. So these 2 guys will have been taken out here. So that's how you do that. I do want to do one last thing here then, and I want to go back and show you. Remember, we've got this template called correlation and SLR, and it's a little template that I made up for you to do correlation using Spearman's and Pearson's. It'll also do simple linear regression and show you the residuals. So that is that blue text file, which is in supplementary files, that folder. And what I've done is I've just copied over the pages here that we need. So this particular page here, and then the normality page right there. So what I'm going to do is I'm going to go back to the push-ups. I'll have to go to this one here because I want to start with all 12 observations. So I've got my ages, I've got my push-ups. Make sure that you've got your X before your Y, because that's the way that this is set up over here. And I'm going to paste this. So paste the values, and this is what we end up with. Now, we've seen this before when we were dealing with correlation. So we have an R here of minus 0.631, a critical value, a computed T-star value, and you reject HO. We also took a look at the Pearson's correlation, and this is what the thing would look like. Okay, actually I don't think we did that one in Unit C, but you could do that by hand and check your work on that. But here's what we do here is we stick them into this particular page here, and then we turn to the normality page. Now this is the Anderson-Darling test of normality for both the X and the Y. Now they're going to both have the same N, of course, because they're paired. If the N is at least 30, then the CLT kicks in and you don't have to worry about the results of the test down here. But if N is less than 30, you do need to go down here and notice that there's a different test for the X's and a different test for the Y's. So for the X's, for the age, you do not reject HO. HO says that the X is normally distributed. So that's good. That passes normality. Same with the Y. So we do not have a problem with normality. And that means then that we can be using the Pearson's correlation test rather than the Spearman's. And we can also use then the regression output. So I've got the regression over here. I'm going to make this a little bit smaller so we can get this all on one page. Okay, so this is what we've got here. So here's your R-squared value, your SE value. I don't have the ANOVA table in here because it doesn't give you any more information that you need than isn't explained in this down here. Well, we've got basically the bottom line of the usual regression output here. All right. Now, down here, I've got the standardized residuals, and I've set up the program that it would show you the most extreme standardized residual. And so, let's just go and get rid of that right here, and everything will change for you. We still have an extreme standardized residual, and so let's get rid of that. And now, the most extreme standardized residual is this one, but that's within range. And I've got a note down here that says this is within range. All right. I do have a note down here saying here's the most extreme standardized residual. There's one of these values. Sometimes you'll end up with two standardized residuals which are outside of 2 and they're exactly the same. And so you would then get rid of both of them at the same time, or all 3 of them, or whatever it is. All right, but again, you only do them one at a time unless they are equal. Anyways, that's how you do that. Notice actually that our normality still holds over here. We're good. And so this is a better regression that we have right here in explaining X and Y. Okay, last thing, I'm going to go through this fairly quickly here, but let's take a look at the price and size example. This is from page S7. And so here's what the output looks like. And this is the graph. If you were to chart this thing out here, we've got the size of the house in hundreds of square feet, and then the price in thousands of dollars. And it looks like this. Okay. If we take a look at the summary output here, you'll notice that there's an R-squared value of 51%. That is significant at a 5% level of significance according to the p-value for the f-test, which, because this is a simple linear regression, one x variable, will be exactly the same as the p-value for size. So there's a significant relationship here. The standardized residual shows that there is a value here which is outside of 2. So I'm going to go back here And we're just going to walk through this thing again fairly quickly. So data analysis, regression. Now this, I've still got all of the boxes filled in from the last one, so I'm going to have to change these and say that here's my price, that's my y variable, all right. My x variable is size, and then everything else is fine except for the output range here. I'm not going to do it way down there. I'm going to move that up to about here. Well, I guess I can put it up there. Good. So here's your 51.4%, which I showed you on the other page here, and the usual kind of stuff, 0.045, 0.045 for the p-values, but I'm interested in the standardized residuals. So let's go down here, and I'm going to sort that and go down here, and we'll notice that the observation number 8 has a standardized residual outside of plus or minus 2. So we're going to get rid of the 8th observation, which happens to be this last one, like that. Let's run it again. Data analysis. I've gotten rid of 1, so instead of going from 9, I'm going to 8. And this will be down here. And we end up with, ooh, R squared really jumps up to 84% here just by getting rid of 1 observation. Let's see if we have any standardized residuals outside of the range here. Notice that the equation changes here. I didn't really show you that above, but the equation does change. And let's see, do we have any standardized residuals outside? And it looks like we don't. So we're good. Actually, that's where we would stop. So that's how you would do that one. You notice by getting rid of 1 observation, your R squared jumps really high, up to 84% from 51%. Now, the last thing here is, well, let's do that actually using the template here for correlation and regression. So let me get rid of these guys and go back and grab those. So that's the push up. I'll have to use these guys here because I got rid of 1 observation. Okay. So copy that. Good. And so we get our 51% up here, and everything else is the same. However, let's take a look at normality. We got a problem with normality. The n is less than 30, so we need to take a look here at, for each of these, whether you reject HO, and we do actually in both cases here, so normality doesn't hold. So what that means then is that we really shouldn't be using regression here. We should be going back here then and, whoops, just looking here, and that's all we can say. We can't express a regression equation. We can just use these guys down here. So the Spearman's correlation, there is a positive correlation between x and y. So as the size increases, so does the price. We know that by a positive R. It's significant. Depending on whether this is a one-sided or two-sided test here, you may hypothesize that we would expect this to be a positive relationship, but that's up for the decision maker to tell you that. And that's what we've got here. But we don't want to be looking at the regression output because normality fails.